collision changed Earth's history in an instant. The sky was swallowed by dust and ash. Sunlight faded, and the cycle of day and night began to break apart. The world fell silent. The roar of the dinosaurs vanished, and the ancient world faded into history. And then, just when everything seemed to be over, life began an entirely different rise. For more than 165 million years, dinosaurs ruled the planet with absolute dominance. They survived fluctuations in sea level, periods of elevated carbon dioxide, and volcanic cycles that lasted for millions of years. Then, within a remarkably short span of time, Earth's entire biological trajectory was violently disrupted, leaving no organism with the ability to respond. This was not an ordinary biological catastrophe. It was a physical event on a planetary scale. Shock waves radiated outward at supersonic speeds, transmitting immense energy through Earth's crust and mantle. Seismic models suggest that the planet shook more violently than during any earthquake ever recorded in human history. An event best described as a planet-wide seismic convulsion. Trillions of tons of rock, fine mineral dust, and, most critically, sulfur-bearing compounds from sulfate-rich bedrock were blasted upward into the stratosphere and beyond. As this material re-entered the atmosphere at extreme velocities, a near-simultaneous global phenomenon unfolded. Earth's surface was engulfed in a thermal rain, where air temperatures surged high enough to ignite dry vegetation. Geological evidence indicates that wildfires erupted across most continents, not because flames spread rapidly, but because ambient heat itself became unbearable. The oceans were not spared. Massive tsunamis, hundreds of meters high, radiated outward from the impact site, sweeping across coastal regions. Crucially, the dinosaurs did not die in the instant of impact. But the Earth that followed was no longer the planet they had evolved to survive on. Immediately after the impact, geological studies indicate that trillions of tons of fine silicate dust, mineral ash, and sulfur compounds were hurled into the stratosphere and mesosphere. Within the first few hours, daylight began to fade in unnatural ways. This was not a sunset. Across vast continental regions, light levels dropped to something resembling a prolonged twilight. Soon after, the sun became nearly invisible to the naked eye. Climate models based on KPG boundary sediments suggest that atmospheric light transmission may have fallen below 5%, and even lower in regions directly affected by the densest dust clouds. As high-altitude ejecta re-entered the atmosphere at tremendous speeds, they triggered a rare global phenomenon, atmospheric heating from re-entry. Billions of tiny fragments glowed red-hot as they collided with air molecules, creating a near-simultaneous fire rain across the planet. These were not large meteors, but countless short-lived streaks enough to heat the lower atmosphere and sustain elevated temperatures during the first critical hours, even as sunlight was already blocked. At the same time, sulfur dioxide released from sulfate-rich rocks at the impact site rapidly reacted with atmospheric water vapor. Within mere tens of hours, this chemistry produced sulfuric aerosols, microscopic acid droplets, capable of reflecting sunlight with extreme efficiency. Then the rain began, but this was not life-giving rain. Sulfuric acid rain formed as sulfur aerosols merged into clouds and precipitated back to the surface. Sulfur isotope evidence in KPG sediments reveals a phase of global acidification occurring within days to weeks after the impact. On land, soils were stripped of nutrients, while vegetation already damaged by fire suffered a further chemical assault. In the oceans, especially near the surface, rapid acidification placed severe stress on calcium-shelled plankton. More dangerous still, the biosphere's fundamental energy source was cut off. Photosynthesis, the process that powered nearly all terrestrial food chains, and much of the ocean began to fail on a massive scale. From the moment the sky disappeared, Earth entered the most dangerous phase of the entire extinction event. And it was within this prolonged darkness, when photosynthesis ceased on a global scale, that food webs would begin to collapse from their very foundations. When the last dust finally settled and sunlight began to pierce a cleansed atmosphere, Earth emerged as a different planet, alien even to its own history. Ecological structures that had remained stable for tens of millions of years were gone. In their place stood an open, sparse world, where life was forced to relearn how to organize itself from the most basic foundations. In the first millennia after the KPG boundary, the planet's surface bore the unmistakable marks of an ecological reset. Pollen and spore records from multiple continents reveal a global fern spike. Ferns require no animal pollinators, spread rapidly, and thrive in nutrient-poor soils. Their temporary dominance shows that Earth had fallen back into a primitive post-catastrophe state, where speed of recolonization mattered more than complexity. The flowering forests that once blanketed the continents could not return immediately. The soil itself needed time to recover its structure and nutrients. The climate during this period remained unstable. Although sulfuric aerosols and fine dust declined significantly, the global climate system required tens of thousands of years to reach a new equilibrium. Sedimentary records point to fluctuations in temperature and atmospheric CO2 as the carbon cycle was disrupted. Photosynthesis remained weakened for extended periods, while weathering and geological activity continued to inject carbon into the atmosphere. Earth entered the Paleogene not through an instant rebirth, but through a slow, planet-wide process of adaptation. Within roughly 100,000 years, surviving populations began to spread. Small mammals, once confined to narrow ecological margins, now faced a planet that was nearly empty. They did not replace the dinosaurs, they explored a new world. Diversity increased slowly but steadily, built on energy-efficient strategies, behavioral flexibility, and omnivorous diets. Experimental forms appeared and vanished. Evolution at this stage was a process of exploration, not a race towards size or dominance. It took 1 to 2 million years for terrestrial ecosystems to begin stabilizing. Flowering plants gradually reclaimed a central role, constructing new forests that were lower, more open, but more efficient under post-catastrophe climates. At the same time, mammals entered an evolutionary radiation, diversifying in size, dentition, lifestyles, and behavior. This was not a chaotic explosion, but a selective, unfolding within a transformed environment. By roughly 10 million years after the KPG event, Earth displayed a new pattern of biodiversity. No single organism dominated absolutely for long periods. Ecosystems were defined instead by numerous smaller niches, flexible energy flows, and an ability to reorganize as conditions changed. In the oceans, food webs were rebuilt from new foundations, favoring groups whose survival strategies matched a more variable world. Life did not return to its starting point. It moved forward along paths that had never existed before. The history of life entered a new chapter. one that forces us to confront the meaning of catastrophe, not merely as an ending, but as a beginning purchased at the cost of an entire lost world. It became a world shaped by quiet survivors, small, adaptable, low-energy organisms that had once lived in the shadows of giants. The first defining trait of the survivors was small body size. Fossil evidence shows that most mammals that made it across the KPG boundary weighed only a few dozen to a few hundred grams, roughly the size of mice or small squirrels. Smaller bodies meant lower energy demands, longer fasting tolerance, and the ability to survive on poor quality food sources such as insects, organic debris, dry seeds, or carrion. In the post-impact world, this became a decisive advantage. A nocturnal lifestyle also played a critical role. Long before the dinosaurs vanished, many mammals had been pushed into nighttime activity to avoid competition and predation. When daylight weakened dramatically and temperatures dropped, species already adapted to darkness. With low-light vision, heightened hearing, and a strong sense of smell were far better suited to survive than animals heavily dependent on daytime vision. Another key factor was thermoregulation in a cold, highly unstable environment. Warm-blooded animals can maintain physiological activity independently of ambient temperature. This allowed them to keep foraging, reproducing, and protecting their young even as the climate turned harsh. This combination of traits explains why mammals survived at far higher rates than large terrestrial reptiles. However, mammals were not the only group to endure this dark interval. Birds, the direct descendants of avian dinosaurs, were also among the crucial survivors. Fossil records indicate that only certain bird lineages crossed the KPG boundary, primarily small species that were omnivorous or seed-eating, capable of agile flight, and able to migrate long distances in search of scattered food. Large birds, specialized predators, or species tightly dependent on green vegetation nearly vanished completely. This underscores a consistent principle. High specialization increases extinction risk during prolonged crises. In freshwater and semi-aquatic ecosystems, survival rates were even higher. Turtles, crocodilians, snakes, lizards, and many freshwater fish appear continuously in post-KPG sediments. These animals have low metabolic rates, can endure long periods without food and often live in environments less directly tied to surface photosynthesis. Rivers and lakes continued to receive organic matter from land and decomposing organisms, providing a more stable energy base than the oceans, where food webs were more severely disrupted. The ability to take shelter was another critical survival advantage. Species that could burrow, live underground, inside hollow trees, or underwater were shielded from extreme thermal and chemical fluctuations at the surface. Burrows offered more stable temperatures, higher humidity, and protection from acid rain during the earliest stages after impact. This allowed many small animals to survive the harshest phases of the post-impact climate. All of these traits converged most clearly in early mammals. Before the KPG event, they were small, inconspicuous creatures living entirely in the shadow of dinosaurs. After the boundary, the very characteristics that once made them seem inferior became core evolutionary advantages. Relatively large brains enabled behavioral flexibility and rapid learning. Diverse teeth supported omnivorous diets. Fur helped retain heat, and short reproductive cycles allowed populations to rebound quickly as conditions improved. They did not dominate immediately, but they endured when much of the living world did not. Life does not need brute strength to survive a crisis. It needs flexibility and energy efficiency. If our own civilization depends on complex, stable energy systems, are we truly resilient? Or are we simply living through a rare and fortunate window in Earth's long history? In every ecosystem, energy flows in one direction. From primary producers, plants and photosynthetic plankton upward, to higher levels of consumers. The critical point is this: food webs do not collapse instantly. On land, herbivores were the first to reach the limits of survival. Plants could no longer grow. Young leaves, fresh shoots, and grasses, the most energy-rich food sources, disappeared. Large animals, requiring tens to hundreds of kilograms of biomass each day, quickly entered a state of prolonged energy deficit. Fossil evidence shows that plant-eating dinosaurs, despite their former dominance in both numbers and size, vanished relatively quickly from the stratigraphic record. Once the herbivore layer collapsed, predators entered their final, short-lived phase of existence. During the first weeks and months, the carcasses of herbivores provided a temporary source of energy. But this supply was finite. When prey populations fell below a critical threshold, large predators, those with the highest metabolic demands, could no longer sustain body temperature, activity, or reproduction. This explains why apex predators experienced near total extinction. The very traits that once ensured dominance, large bodies, powerful musculature, complex nervous systems, became liabilities in an energy-poor world. In the oceans, the collapse followed an even clearer logic. Photosynthetic plankton, the foundation of marine ecosystems, declined sharply as light levels dropped below what was needed to sustain photosynthesis. This was followed by the collapse of heterotrophic plankton, then by filter feeders such as mollusks and small crustaceans. Small fish disappeared first. Larger fish followed. Marine food webs, which had remained stable for tens of millions of years, broke apart from the bottom up, leaving unmistakable gaps in the fossil record. One of the strongest lines of evidence for this collapse is the complete extinction of ammonites and belemnites. These cephalopod groups had dominated Cretaceous oceans, were globally distributed, and had life cycles well adapted to stable environments. However, they were tightly dependent on high-energy marine food webs. When plankton collapsed and ocean chemistry shifted toward acidification, these groups lost their ecological foundation and vanished entirely from Earth. In contrast, some organisms with more flexible survival strategies showed much higher survival rates. Freshwater fish, turtles, crocodilians, and certain amphibians were not directly dependent on complex marine food webs and could endure long periods without food due to low metabolic rates. Freshwater ecosystems, with shorter food chains and continuous input of organic matter from surrounding environments, became temporary biological refuges. This is why fossil records consistently show significantly higher survival rates in freshwater systems than in the oceans or arid terrestrial landscapes. The more complex an ecosystem is, and the more it depends on multiple stable links, the more vulnerable it becomes when a foundational link is removed. Simpler systems, with fewer energy levels and more flexible survival strategies, are better able to reorganize quickly under extreme conditions. As the planet entered its new state, darkness became the default condition. Fine silicate dust and sulfuric aerosols, blasted into the stratosphere by the Chicxulub impact, did not fall back to Earth like ordinary volcanic ash. At these altitudes, where rain cannot wash them out, they remain suspended for long periods, continuously reflecting and scattering sunlight, sharply reducing the energy reaching the surface. Under these conditions, photosynthesis did not merely weaken but nearly came to a halt on a global scale. On land, plants remained standing, but they survived only on the final reserves accumulated before the catastrophe. In the oceans, where light is already weak at depth, the catastrophe unfolded faster and more completely. Photosynthetic plankton, the engines of marine energy, depend directly on surface light. When light intensity dropped below a critical threshold, their populations collapsed. Without plankton, filter feeders lost their food source. Small fish died first, followed by larger ones. Fossil and geochemical evidence shows the collapse propagated upward from the base of the food web. Prolonged darkness simultaneously triggered a climatic shock. With incoming solar radiation blocked, Earth continued to emit infrared energy into space according to physical laws. Climate models reconstructed from KPG boundary sediments indicate that global average temperatures may have fallen by 10–15 degrees Celsius, and even more across continental interiors. Uneven cooling amplified day-night temperature swings, creating physiological extremes that most Cretaceous organisms had never encountered. Frost appeared at lower latitudes than usual. Many regions once warm slipped into prolonged cold. At the same time, acid rain continued its assault. Sulfuric aerosols mixed into clouds and precipitated out, leaching nutrients from soils and weakening the recovery potential of the remaining vegetation. In the oceans, surface water acidification reduced calcium carbonate saturation, triggering a crisis for shell-forming organisms. The fossil record documents the complete disappearance of ammonites and belemnites during this interval, not due to direct impact, but because the environment no longer provided sufficient energy and favorable chemistry to sustain their complex biological structures. When photosynthesis stopped, every food chain lost its source. Herbivores vanished first. Carnivores survived briefly on carcasses, then ran out of fuel as well. Extinction did not occur all at once, but spread layer by layer, from species directly dependent on plants to apex predators. body size became a lethal disadvantage. Large organisms require high energy intake to maintain heat and activity. In an energy-poor world, biological efficiency mattered more than strength. Small species with low metabolic demands, capable of prolonged fasting or shifting to omnivorous diets, had a chance to endure. Natural selection in this phase did not reward dominance. It rewarded economy and flexibility. The KPG catastrophe was not merely an impact, but a restructuring of the biosphere. As energy slowly returned when aerosols settled out, Earth did not revert to its previous state. Most links in the old system were gone. Ecological niches stood empty. The survivors, few but adaptable, faced a new world, colder, poorer in energy, and no longer ruled by giants. The extinction of the dinosaurs was not merely a localized full stop, but a sweeping reconstruction on a global scale. After the fateful impact at Chicxulub, Earth did not collapse entirely. It entered a phase of ruthless purification. As the atmosphere was sealed off by dust and sulfur, photosynthesis stalled, triggering a cascading collapse of food chains from the oceans to the continents. Yet within that very moment of total devastation, a new world order began to take shape from the ruins. When the last dust particles finally settled after tens of thousands of years, sunlight returned, igniting a remarkable recovery of plant life. Mammals, once small, hidden, and marginalized, began a powerful evolutionary surge during the Paleogene. Freed from the pressure of gigantic predators, they rapidly diversified in size and adapted to environments ranging from dense forests to open grasslands. What followed the catastrophe was not simply death, but the greatest transfer of dominance in geological history. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.